Periodic trends we describe as periodicity. This just kind of is what repeating patterns do we see over and over in the periodic table, okay, or a predictable pattern that changes as we go either across or down the periodic table. Now, there's always exceptions to these trends. They're just in general, this is what we see. So there might be one or two that don't fit exactly, but in general, these are the trends that we see. Okay, so the first trend we're going to look at is atomic radius. So we need to define that. It's halfway between the nuclei of two bonded atoms. So if we take the center and define that as our nuclei, okay, the atomic radius is from here in the center to here, just like it would be for any circle. Okay, so if the distance between two of nuclei would be this whole line, okay, half of that distance is a radius, so half of this. Okay, so that's what we're talking about, is pretty much how big around the radius is. Okay, so the trends that we see here are that as you go across the periodic table, the trend decreases. So that means that our atoms get smaller. Okay, as we go down, they get larger. Okay, so you can see that with this picture. As you go across, lithium is much bigger than fluorine, and as you go down, hydrogen is much smaller than francium. So we need to talk about why does this happen. Okay. Well, as you go across the periodic table, the number of protons increases, okay, as so does electrons and neutrons, but the protons increase. So that means you have more positive charge here inside your nucleus. So if you have more positive charge here, that means these electrons are going to get pulled in tighter to the center of the atom. Okay, so beryllium here has more protons than lithium, so beryllium is going to be able to use the positive charge here in the nucleus to pull these electrons in even tighter. Okay, so as that pull becomes greater, this is called the nuclear charge, the attraction between the nucleus and these electrons gets stronger and stronger, so it pulls the electrons in tighter. And that's why we see this trend here of our atoms being larger here, fewer protons, so there's not as much nuclear charge, not as much pull. Here, there's 9 protons, with lithium only had 3 protons. Okay, fluorine has 9 protons. There's a lot more nuclear pull, so it pulls the electrons in tight and makes this small atom. Okay, so that's how it works going across. Going down, we're adding these shells. Okay, so if this is 1s, this is 2s, this is 2p. Okay, so we keep adding these levels. If this is lithium, over here we've got our 1s, 2s, 2p, 3s, etc. Those continue to add as we go down. So as we go down, there's more and more and more energy levels. So even if there is a really tight pull here from our protons in the middle, there's all these extra layers, and so they can only pull in so much, and so these atoms are bigger. So as we go down, that is why our atoms are larger. So if you look at lithium, okay, or hydrogen even here, very small because there's only a 1s. When we get down here to francium, okay, we've got 1s, 2s, 2p, 3s, 3p, 4s, 3d, etc., all the way down to 7s here in those shells. So the more shells we have, the bigger the atom is going to become. Okay, so that explains the radii. Ionization energy, definition of that is the energy needed to take away an electron. Okay, so if we think about our atoms at the top of the periodic table being very small, okay, if this is our positive and then we've got an electron right here, okay, the pull or the attraction between this is going to be very strong. If we have something that has several levels, okay, and our electron is way out here, and this is our proton, this distance is pretty big. It's going to be a lot easier to take away this electron because this distance is large, and it's going to be much more difficult to take away this electron because the distance is small. So the smaller atoms are going to have a higher ionization energy. It's going to take more energy to get those electrons away than the ones from the large atoms. Okay, so that will help explain these trends. So as we go across here, we talked about how these atoms are bigger, these are smaller, so it takes more energy to get this electron away here than it does this one over here because this one is further away from the nucleus. So the energy increases as you go across. It's more difficult to take away an electron that's closer to the nucleus. And then as we go down, again down at the bottom, these are going to be much larger. So our electrons are going to be further away from our nucleus here. So these are going to be easier to take away. So the energy decreases as we go down because our atoms get larger. Okay, so that's how ionization energy works. Okay, and this is an explanation of that. Left to right, the radius decreases. Okay, so the protons have more pull on the electrons, so it's more difficult to take away, or it's higher ionization energy. Okay, the smaller they are, the more difficult it is to take away. And this one's the one going down, where you can see here again this electron is much further away from the nucleus here than the one over here in lithium. Okay, so when this distance is shorter, this one has higher energy, this one has lower energy. Okay, so sodium is lower on the periodic table, less pull, less ionization energy. And then the last trend we're going to talk about is electron affinity, and this is the energy that's given off when an electron is added. Okay, so now we have to think about which atoms want electrons. Well, if we think about it, metals have positive charges, so they're giving away electrons. Non-metals over here have negative charges because they want electrons. So when we have negative charges as a non-metal, okay, they're going to release more energy because they're the ones that are going to be adding electrons. Okay, so we want to think about that. So again, when we look at this, -1 charge, -2 charge, -3 charge. These are adding 1 electron, adding 2 electrons, adding 3 electrons. So there's going to be more energy over here than there is over here where the metals are trying to get rid of electrons and become positive. So these are +2 and +1. Okay, so again, wherever you're attracting electrons, the energy, or excuse me, the electron affinity is going to be higher. So again, moving left to right, the radius decreases, more proton pull, so the electrons are closer. Okay, so they're going to give off more energy as they release an electron. As we go down, as you move down the group, the radius increases, more shells again, so those outer electrons are going to be farther from the nucleus, so they're going to have less pull, so less energy to add an electron. And then the last thing we're going to look at is just some real quick definitions. Remember that ions are atoms with a charge, cation. Okay, I always remember there's a T here, it looks like a plus, so those are the positively charged ions, and anions are the negatively charged ones. So if we look at a lithium atom versus a lithium ion, the atom's going to be larger because the ion has lost an electron. Okay, so when we have a positive ion here, it's going to be smaller because it's gotten rid of an electron. Okay. Negative is the opposite. Here we've gained 2 electrons, okay, because we have a -2 charge here. So when we gain electrons, the radius gets bigger with a negative ion. Okay. So go ahead and go through, write your answers for this, and then we'll go to the next slide, and then you can check your answers. Okay, so pause the video for a minute, write down the order of lithium, cesium, potassium, and an order of increasing radius, ionization energy, and affinity, what you think, which one's going to have the smallest radius, then the next biggest, and then do the same thing for lithium, nitrogen, and carbon. Okay, so pause. And here are the answers. Okay, lithium is the smallest because, the smallest because it's the highest up on the periodic table. Cesium's the largest because it's the lowest, it has more energy levels. Smallest amount of ionization energy is the biggest, so cesium's first, and then potassium, then lithium, and electron affinity follows the same. Okay, cesium is the biggest, so it's not going to want an electron as much as lithium. And then lithium, nitrogen, and carbon. Now we're going across. Lithium is going to be the biggest in this case. The furthest one over is nitrogen, so nitrogen is the smallest because it's the furthest to the right, then carbon, then lithium. And then when we look at ionization energy, the least ionization energy is going to be your biggest atom, and then your most ionization energy is going to be your smallest, and electron affinity works the same way. Your positive ions are going to have lower affinity, your more negative ones are going to have the most. And those are your periodic trends.